Atmosphere of Io. Atmosphere of Io refers to the extremely thin blanket of gases surrounding Jupiter's third largest moon Io. The atmosphere is primarily composed of sulfur dioxide, SO2, along with sulfur monoxide, SO, sodium chloride, NaCl, and atomic sulfur and oxygen. Atomic O2 is also expected to be present. Io is considered to be the most volcanically active body in our solar system. Pele-type volcanism is believed to be the cause of sulfur components in the atmosphere. Volcanic plumes pump 229 pounds of SO2, sulfur dioxide, per second into Io's atmosphere on average, though most of this is deposited back onto the surface. Sunlight sublimates this solid SO2, turning it into the gaseous state and creating a thin atmosphere. Due to this, atmospheric pressure is significantly higher near volcanoes, about 0.0000000005 to 0.00000004 atmospheres, around 5,000 to 40,000 times larger than that of the night side of Io. Apart from this, minor components like NaCl, SO, O are also formed by other processes. The main source of NaCl and KCl is thought to be volcanic. Some volcanic vents are thought to expel NaCl and KCl but little to no SO2. Sputtering of the surface by charged particles from Jupiter's magnetosphere is thought to be the origin of the NaCl, SO, O, and S. They are also formed from direct volcanic outgassing. Photodissociation is thought to be the origin of SO, Na, K, and Cl. Photodissociation plays an important role in the atmosphere at higher latitudes. Because the process happens more often during daytime, the concentration of Na is believed to be higher during daytime. SO2 is the main constituent, comprising 90% of the atmospheric pressure. About 3 to 10% is SO. The atmospheric pressure varies from 0.0000000003 to 0.0000000003 atmospheres, seen on Io's anti-Jupiter hemisphere and along the equator, and temporally in the early afternoon when the temperature of surface frost peaks. On the night side, SO2 freezes, decreasing the atmospheric pressure to 0.00000000000009 to 0.00000000000009 atmospheres. Some studies suggest that the night side atmosphere consists of non-condensable gases like atomic O and SO. The atmosphere on the side facing away from Jupiter is not just denser but also extends over a greater range of latitudes than the side facing Jupiter. The vertical column density at the equator ranges from 1.5 times 10 to the power of 6 cm squared at sub-Jovian longitudes to 15 times 10 to the power of 6 cm squared at anti-Jovian longitudes. On the surface, sulfur dioxide is in vapor pressure equilibrium with frost. The temperatures increases to 2,780 degrees at higher altitudes where the lower atmospheric density permits heating from plasma in the Io plasma torus and from Joule heating from the Io flux tube. The day-side atmosphere is mostly confined to within 40 degrees of the equator, where the surface is warmest and most active volcanic plumes are found. The polar atmospheric pressure is only 2% of the equatorial atmospheric pressure. At about plus or minus 40 degrees latitude, the atmospheric pressure will be half of that at the equator. The atmospheric density increases the closer Io gets to the Sun. Farther away from the surface, higher the concentration of O and S2 gets. This is because of the lower mass of oxygen and sulfur atoms compared to others. The O-SO2 ratio is estimated to be between 10 and 20% in the upper atmosphere. These gases exist up to a distance of 10 times the radius of Io. Io has a sodium tail similar to the sodium tail of the Moon. Io also has an ionosphere with a density of 2.8 times 10 m-cubed at 49 miles altitude, comparable to the ionospheres of Mars and Venus. Occultation studies by Pioneer 10 revealed that the night-side ionosphere is significantly less dense for the first time. Based on the 6 occultations conducted by the Galileo probe in 1997, the ionosphere is asymmetrical. The plasma density varies by longitude. The interpretation of the observations assumes that the increased plasma density is distributed in a spherically symmetrical bound ionosphere with a dense downstream wake. Depending on the location, peak densities of about 5 times 10 m-cubed were found, reaching a maximum of about 2.5 times 10 m-cubed in one of the occultations. Due to its thinness, Io's atmosphere does not cause that much effect on the surface, other than moving SO2 ice around and expanding the size of plume deposit rings when plume material re-enters the denser dayside atmosphere. Every second, almost 1 ton of gases escape from Io's atmosphere into outer space due to Jupiter's magnetosphere. Due to this, the atmosphere should be constantly replenished. These gases orbit Jupiter along with Io, creating a Io plasma torus. Io's atmospheric density is directly related to surface temperature. When Io falls into the shadow of Jupiter during an eclipse, the temperature falls. This causes deposition of the SO2, and results in an 80% decrease in the atmospheric pressure. This increases the albedo of Io, thus Io appears brighter when covered with frost immediately after an eclipse. After about 15 minutes the brightness returns to normal, presumably because the frost has disappeared through sublimation. Post-ecliptic brightening can be observed with ground telescopes. Cassini spacecraft captured post-eclipse brightening in near-infrared wavelengths. Further evidence for this theory came in 2013 when the Gemini Observatory was used to directly measure the collapse of Io's SO2 atmosphere during, and its reformation after, eclipse by Jupiter. Io hosts aurora events, even though the atmosphere is extremely thin. Unlike other celestial bodies where an aurora occurs at the north and south poles, aurora on Io occurs near the equator. This is because auroras on other bodies are caused by the interactions of the body's magnetosphere with the solar wind. In contrast, Io has no magnetic field of its own. Instead of solar wind, charged particles from Jupiter's magnetosphere interact with Io's atmosphere, creating auroras. Sodium atoms cause a green glow in the aurora. Here blue glows caused by SO2 are nearer to the surface than red glows caused by oxygen. This is because SO2 is heavier than oxygen, and as a result will be more gravitationally bound to the surface. Due to this, red glows reach up to a height of 500. The aurora moves across Io, as it changes its orientation with respect to Jupiter's magnetosphere as it orbits the planet.